Okay, so we are very happy to have Calin Martin from Vienna, and he's going to talk about the Atlantic Circumpolar Current. All right, it's all yours, Calin.
Yeah,
thank you.
Thank you very much for the introduction, and also let me thank the organizers for the opportunity to give this talk. I'm going to speak about a joint work with Ronald Kirchmeier from the University of Vienna. And so as announced, I will speak about exact solutions concerning the Atlantic Circumpolar Current, shortly ACC. And so this is a recent published result. So we were somehow amazed by the Atlantic Circumpolar Current (ACC) mainly by its properties. So this current is the only current that completely encircles the globe. It flows almost unobstructed by land masses, being constricted only in the Drake Passage, flowing around Antarctica, and its massiveness, it's reflected by the large volumes of water that it transports, and these effects are felt from the surface to deep down as much as 4 to 5 kilometers. ACC is about 23,000 kilometers long, and in places it may extend over 2,000 kilometers. This flow is an eastward flowing jet, and this results in large interbasin transfers of heat and mass. And this is an aspect that it is of central importance in ocean's role in climate. So, so this is a picture of ACC showing the two main fronts, the subantarctic front and the polar front, ACC being in the region in between. So here in black is Antarctica. And what we are going, the main aspects of this talk would be the derivation of a family of exact solutions describing a flow that moves completely around the globe on a circular path, and such a property we saw, it's a characteristic for ACC. So these flows, this type of flows are azimuthal flows, and they follow a small circle, allowing for a meridional jet structure, which decays monotonically with depth. The velocity profile and the pressure are given as functions of the variables involved from the free surface to the bottom. So they are functions of depth and angle of latitude. And so this study comes at a moment where previous nonlinear studies for oceanic east-west propagation have been based on approximations of F-plane and beta plane type. That means that the Earth's surface is taken to be approximated to its tangent plane, more or less. However, the nonlinear exact solutions that we construct, they retain the effects of the spherical geometry of the Earth, and they possess a discontinuous density stratification. So the density stratification in ACC was pointed out in a paper by Karsten and Marshall from 2002, and they hinted to the possibility of existence of a thermocline in ACC. And so this vertical layer of the flow gives rise to an interface that plays the role of an internal wave. So in order to reach our goal, so we start from the Euler equations, allowing from a non-conservative force field. And these Euler equations are written in spherical coordinates, in a system of spherical coordinates that rotates with the Earth. So we are incorporating geophysical effects here. And in doing so, we actually adapt an approach by Constantine and Johnson from 2016. So we extend their approach to the setting of discontinuous stratification. Actually, the new aspect here is the presence of a discontinuous density, as emphasized earlier. So let me get to the spherical coordinate system. So we will work in r, theta, and phi. R is the vertical variable here, representing the distance to the center of the Earth. And theta is the polar angle, representing the latitude. And for the purposes relating to the ACC, theta is supposed to lie in this I theta interval, 3 pi over 4 minus pi over 18, up to 3 pi over 4 plus pi over 18. Phi denotes the azimuthal angle, and ER, E theta, and E phi is our right-handed coordinate system that is located at a point on the surface of the Earth that rotates with the Earth. So we will denote with bold face U the velocity. So actually the component along the ER vector is denoted W. This is the vertical velocity, and V is the velocity along E theta, so in the longitudinal direction, and U is actually the most important aspect here, is the velocity, the azimuthal velocity, the azimuthal component of the velocity vector. So this will be from east to west, and P of r theta and phi denotes the pressure. So because we want to deal with a discontinuous density, so the fluid domain will consist of two fluid layers, actually denoted here D1 and D2, and so D2 is from the bottom of the ocean. So let's say D is a function that defines the bottom, and up to some interface denoted here. The interface defining function is denoted with H, and then the other layer starts from the interface up to the surface. Denote the interface, the surface defining function is denoted here with K. So in the most general way, well, they are depending on theta and phi, but for the purposes of this talk here, so this dependence on phi will be canceled later on, so we will see why. And so the motion, so we, as before, as we said, we want to capture, so we want to introduce geophysical effects, or capture the effects of the Earth's rotation. So by associating with this right-handed system of coordinates with a fixed point on the sphere, which is rotating about its polar axis with some constant speed omega. Yeah, and then so doing so, we need to add Coriolis terms, these two omega cross U, and centripetal acceleration, omega cross R. So omega is the capital. I mean, this boldface omega is the vector, and this is the absolute value. So then the equations of motion will contain. The Euler equations of motion will contain additionally these terms here. So in explicit notation, so we have the momentum conservation, or the Euler equations. So these are the equations written in spherical coordinates. The terms on the right-hand side, the terms here in blue, on the left-hand side, they are the Coriolis terms plus the centripetal acceleration. So this is just, so this is the system of equations describing the momentum conservation. So here on the right-hand side, we have the pressure gradient. So P denotes the pressure gradient, and these are derivatives with respect to the vertical variable, with respect to the longitude variable, and with respect to the azimuthal variable. And with F, R, F theta, and F phi, this is the body force vector. And here, the body force vector contains well, a gravitational term. So instead of this R here, this should be a G. So I apologize for this. So this is a minus G here, minus small g, which is the acceleration of gravity. Then this capital G of R and theta is a general function that is allowed here in the system and represents a non-conservative body forcing. And this rho, depending on r and theta, is the density. So we assume that the density is given and it is dependent on the depth and latitude. And the task at hand is to derive a formula for the velocity field and for the pressure. And moreover, to determine the interface and the surface. So this is H, the letter H denotes the interface, and K is the surface defining function. Well, the bottom D is supposed to be given. So besides the conservation of momentum, we have the equation of mass conservation, which is roughly the derivative of the density plus the divergence of the vector field, which consists of the density dot with the velocity field. It should be zero. So except for the governing equations, there are boundary conditions. So this is a water wave problem, and this is completely specified when we specify the boundary conditions. So at the surface of the flow, we ask that the pressure equals some given function. So the small p is the unknown of the problem, and the capital P1, this is some given function. So we ask that the pressure equals some given function on the surface. Then there are kinematic boundary conditions, which roughly say that the fluid particles do not cross boundaries, or that the boundaries are really boundaries. So this is the kinematic boundary condition on the surface. Yeah, and it roughly says that the speed of the water is actually equals the speed of the surface, right? So, and then at the interface, we have the balance of forces. So what is required? It is that the velocity field from the lower domain and the velocity field from the upper domain have the same normal components. So actually, so the velocity is continuous in the normal direction across the interface. And moreover, we require that the pressure from below, so this would be the P1 is the pressure from above equals the pressure from below, right, at the interface. Recall that we have the water domain was consisted of a union of the two domains D1 and D2, and in each of these D we have accordingly quantities which are denoted with P1, U1, V1, W1, and as well P2, V2, W2. And moreover, there is a kinematic condition at the bottom, which says again that the fluid particles do not cross the bottom. And having said this, so we are returning to the problem of finding exact solutions to these governing equations. So actually, to mimic what happens in the ACC, we will seek solutions that represent a steady flow. That means we suppress time from the equations, and the steady flows will propagate in the azimuthal direction and with no variations in this direction. So this means that only the azimuthal component is allowed to depend on some r and theta, and the other two components, so the vertical component and the component along the e theta, are asked to vanish. And we ask that the pressure also depends on r and theta. So this is what we understand by a flow that has an azimuthal variation, that it is in the azimuthal direction. So this is the azimuthal component, uj, but it presents no variation in this direction. So it does not depend on the angle phi. So again, we have j here is from 1 to 2, so it corresponds to the two layers into which the domain is divided. And as well, we require that the boundaries of the domain, so K, the surface, and D, the bottom, as well as the interface, they do not depend on phi, so they don't present a variation in the azimuthal direction. And Well, this consideration implied that the equation of mass conservation and the two kinematic conditions are satisfied automatically because the quantities involved there are zero. So let us see here. So this is zero, and then the V's are zero. So and W's are zero. So then everything is satisfied identically. So now let's proceed. So looking for this type of solutions, we know variation in the azimuthal direction. We end up with this system, which is a translation of the Euler's equations after these considerations, and they can be written in this condensed form by this noticing that this common bracket appears in both of the equations, and the question is how to solve this, how to get the formulas for uj and pj. So g here, the small g is the acceleration of gravity, and rho j is the density in the layer dj, and this capital G is the forcing term. This is the forcing term, and r is the vertical variable. So this can be solved very easily by eliminating the pressure, and in doing so, we obtain a transport equation, which is written here, and solving this using the method of characteristics, we end up with the formula for the velocity. So this uj of r at theta is given in terms of this formula. So there are a few quantities here that need some explanation. So this capital J is actually this term r times rho times the body force term, which appears along the e theta vector. And so the other quantities, so they are strictly related to the method of characteristics. So they that we use to solve this. So this is explicitly given. The velocity is explicitly given. These fj are continuously differentiable functions. So actually, for each such capital fj continuously differentiable, we have a velocity uj. So this gives us a family of solutions actually, and now we can proceed to determine the pressure in the two layers by simply integrating in this system here, and in doing so we come up with this formula. So first, the pressure in the lower layer, which was denoted with d2, so is given in terms of this integral where f2, so this f2 is a given function. I mean, no matter how we give f2, we can find the velocity, and then we can find p2, and this f2 of this L and f2, they are given in terms of the body forcing h. So recall that h contains the body force term, and further we can, having the formula for the pressure in the lower layer, we can compute the pressure in the upper layer. So this again, they are given in terms of the velocity. So f1 is the function that appears in the velocity, and then also the f1. So this is a function that depends in this case both on the interface and the theta variable. So it has this long, complicated expression which involves the interface and the body forcing and the function f1 that defines the velocity. So now it's clear that we cannot find a explicit formula for this in general, but what we can do, so from the boundary condition which asks that the pressure equals some given pressure on the surface, so this given pressure actually determines the free surface K and the interface H by this in an implicit way. So this is actually an implicit equation for K and H. So this is again, K is the surface and H is the interface. It appears also here, surface and interface. So once it is apparent from this formula that once the surface is known, the interface is also known. right? Implicitly, yeah. But nevertheless, so the interface can be determined by looking at the balance of forces at the interface. So it requires that the two pressures are equal along the interface. So in order to do this in a mathematical way, we formulate this as an operatorial equation. And to do so, we want to non-dimensionalize first. So we divide by R2 and R1, respectively. So we divide the pressure by the atmospheric pressure, and then finding the interface is equivalent to solving this operatorial equation. So I denote this with the operator G calligraphic, and the so this comes from equating the two pressures along the interface and finding the free surface is equivalent to using the dynamic condition on the surface, which requires the pressure to be some given function there. And then this determines another operator that depends now on on the surface and on the interface. So this operatorial equation is this one written here. So it consists of the pairing between calligraphic G and calligraphic F in this respective value equal to 0. And so we will appeal to the implicit function theorem, which says that once we have a solution, then under certain circumstances, we can find other solutions that are close to localized to this one. So H0 equal to 0 and K0 equal to 0 means that the flow is it has a surface and an interface that follow the curvature of the Earth. So and this is actually a solution of this equation of the system H0 and K0, and denoting with this P01 the pressure which is required to maintain an undisturbed free surface and free interface following the curvature of the Earth. So we will need to show that the derivative of this operator in this basic flow, or the ground state, so to say. So the here 1 0 stands for the interface and 1 stays for the surface that are undisturbed and follow the curvature of the Earth. So the derivative in this is actually, this consists of this matrix of derivatives. So we need to show that this is invertible. And when we compute this derivative, so this is really the formula for the usual formula for derivative. So end up with these quantities here. So F2 and F1 are those given functions that define the velocity field, and L2 and L1 are some other expressions that involve this body forcing and some other integrals. And the term in red is quite explicit. So acceleration of gravity times the difference in densities. And well, it turns out that for some realistic values, so assuming that the velocity, the azimuthal velocity is less than 1 meter per second, and then that the difference in the densities, so this ρ2 minus ρ1 lies between this value 0.2 and 0.5. So it turns out that the term in blue here is less than this 0.02 times R2, and the term in red is greater than this 1.9 R2. And therefore, you see that this quantity here is negative. So, then the operator norm is greater than some positive constant, and because it is really, the derivative is really this nearly the identity operator times this constant. So then it's clearly that this is an isomorphism between these two Banach spaces. And now, remember that we have to compute all these derivatives. So we have established that this is an isomorphism, and further we compute this derivative here. the derivative of calligraphic f. And it turns out that this is something similar, so a function that involves f1, L1, and by using a similar reasoning, so appealing to the fact that this u1 does not exceed 1 meter per second, and comparing with this omega times r1, and then it turns out that this is also some negative quantity. So this would imply that this is an isomorphism. And for the other two entries in the 2x2 matrix, we find that they are 0, and therefore, so this matrix in this ground state, so in this is equals only to this diagonal matrix. So both of these entries is an isomorphism. So therefore, the matrix as a whole is an isomorphism. And now the implicit value theorem tells us that each small perturbation of this P01 pressure, so I recall that this is the pressure maintained to required to maintain an undisturbed free surface and an undisturbed interface. And so for every such small perturbation, there is a unique interface and a unique surface, which is solution to this equation. That is, there is a unique interface, a unique free surface that satisfy our water wave problem. And and so, well, this clearly cannot be determined explicitly in general, but they exhibit some properties that come in agreement with what is observed in reality. So assuming that the velocities, the azimuthal velocities are differentiable, which is saying that this capital F and G are continuously differentiable in each layer, and then that the free surface corresponds to a small enough perturbation of this P01, and then in fact, this will be C1. So if it is continuous, then by applying some bootstrapping argument, it will be C1. And we have that derivative of K greater than 0 implies the pressure, derivative pressure less than 0. And if the pressure, the derivative of the pressure is greater than 0, then the derivative of the function defining the surface less than 0. So this would tell that if the pressure is increasing, then what will happen with the surface? The height will decrease. So this is something what one expects. So, and this is similar for the relation 1. And, some other interesting property refers to the regularity of the interface. So assuming that the interface defining function is C1, so this means it's continuously differentiable, then and if the velocity field is n times continuously differentiable, then actually the interface gains a bit more regularity, so it would gain one more derivative. And similarly, if this capital F and G are infinitely differentiable, then the interface would be also infinitely differentiable. So this is based on the following fact. So recall that this is the equation that gives the interface. So, and differentiating this with respect to theta, we end up with this equation. So now we see that if we manage to show that this coefficient here, A1 plus A2 is not 0, then we can move this to the right-hand side and we can differentiate once again, because this B of theta is something which is differentiable. So, and this A1 of theta is also differentiable. So this is, this B of theta actually consists of these terms here. They are clearly differentiable if this F2 and F1 are differentiable. And now the point is to show that this coefficient is less than 0. So this follows by some similar argument that was used when we proved the existence result. So, so the details are here. So actually, all these quantities can be, for these quantities, we can find bounds by using that we impose on the azimuthal velocity to be, let's say, less than 1 meter per second, and then this quantity here would be less than this 0.04, while A2 is less than minus 1.9 times R2. So then therefore this sum is again negative. So since this is not zero, then we can move this to the right side and divide by it, and we can differentiate once again. So, and now we can use this argument repeatedly to show that indeed, if this f and g are infinitely differentiable, then also the interface is infinitely differentiable. And so I have one more thing to show. So it is possible that in certain situations to determine the interface and the surface explicitly. So let's say that the density in the lower layer is constant, and the density in the upper layer deviates from this constant by this A1R, and these variations in density between the lower layer and the upper layer is between these two values. Then now we choose F1 and F2, and this corresponds to choosing velocity field in the two layers. And then it turns out that this equation that defines the interface, actually the derivative of that equation becomes this one, and this previous one can be written like this. So it's actually this can be integrated. Because these terms are these combinations of sines and cosines, and we obtain the formula for the free surface, the non-dimensionalized interface is given explicitly here. So for these two realistic densities. So I will stop here by concluding by recalling that we constructed an exact solution that represents a flow that moves in the azimuthal direction without variations in that direction. The flow is given in terms of spherical coordinates, so it is a flow that exists on a sphere, and the solution displays a discontinuous stratification, which gives rise to an internal wave, and the solution also admits a velocity profile that varies with depth. We used an approach that starts from the Euler equations, allowing for a non-conservative force field. So these are all a few aspects that were discussed, but many more aspects remain to be discovered. And one of these is, for instance, to derive azimuthal solutions that present azimuthal variations. Oh, thank you very much. Oh, thank you for your attention. Excuse me? Yes, I can hear you, but very, very badly.
Better now?
Yes, what I hear is some repetitive noise. Oh.
Calin?